Section 1.8 Combinations of Functions and Composite Functions. Decide, commit, succeed, unknown. So if we have two functions, f and g, we can add, subtract, multiply, and divide. First, we need to define what it means to add, subtract, multiply, and divide. We're adding two functions, f plus g of x. Then we can write this as f of x plus g of x. If we're subtracting two functions, we can write it as f of x minus g of x. And if we're multiplying, we can write it as f of x times g of x. And then dividing would be f of x divided by g of x, where g of x does not equal to 0. The domain, once we perform these operations, is a set of all real numbers common to the domain of f and g. And so this right here means the domain of f intersected with the domain of g, which just means what do they have in common. Example 1, let f of x equals 4x minus 3 and g of x equals x minus 5. Find each of the following functions and determine the domain for each function. So first, we want to rewrite this the way it's defined. So I have f plus g of x. So I can rewrite this as f of x plus g of x. So here for the function f, we have 4x minus 3, and the function g, we have x minus 5. So I'm going to have f of x, which is 4x minus 3, plus g of x, which is x minus 5. Then we can simplify. 4x plus x would give me 5x, and negative 3 or minus 3 plus negative 5 would give me a minus 8. So the sum of these two functions is equal to 5x minus 8. We want to find the domain. So notice here the domain of f. Here's my function f. Since it's a line, then the domain, there's no fractions, there's no square roots, so the domain will be negative infinity to positive infinity. And then the domain of g, again, there's no fractions or square roots or logarithms. It's a line, so the domain would be negative infinity to positive infinity. So the intersection of these two domains, basically what does this have in common with this? And they have everything in common. So the domain of this function here is negative infinity to positive infinity. Okay, let's look at letter B. So for letter B, we have f of x. We can rewrite this as f of x minus g of x. So f of x in this example is 4x minus 3. That's given here. Minus, I'm going to use a parenthesis, g of x is x minus 5. And you want to use a parenthesis since you're subtracting the entire function. So if we simplify, 4x minus x is 3x. Negative 3 minus a negative 5 will be a positive 5. So negative 3 plus 5 would be plus 2. So f minus g of x is 3x plus 2. And again, the domains here are the same, in negative infinity to positive infinity. So the domain for this function for f minus g is going to be negative infinity to positive infinity. Okay, letter C, we have the product. So I can rewrite this as f of x times g of x. F of x is 4x minus 3, and g of x is x minus 5. 4x times x is 4x squared. 4x times negative 5 is negative 20x, minus 3x plus 15. So the product is equal to 4x squared. Negative 20x minus 3 is negative 23x plus 15. Notice that in our result, we still don't have anything such as a fraction or a square root or logarithm. This is a parabola that opens up, so it looks like a U shape. So that means the domain is still going to be negative infinity to positive infinity. Last, we have the quotient. So we have f of x divided by g of x. So f of x is 4x minus 3. G of x is x minus 5. So f divided by g of x is equal to, we can't simplify any further. So my answer would be 4x minus 3 divided by x minus 5. In our answer here, notice we have a fraction. So to find the numbers that are excluded from the domain, we set the denominator equal to 0. So we get x is equal to 5. So x equals to 5 can't be in domain. So your domain is going to be everything except for 5. So we can write that, I'm going to write it up here. So all the negative numbers all the way to 5. And then starting from 5 all the way to infinity. Okay, so notice I use parentheses to represent that 5 is not included. Example 2. So f of x is the square root of x, and g of x is x minus 13. So here I can write this as f of x plus g of x. F of x is the square root of x, and g of x is x minus 13. Simplify. Square root of x plus x minus 13. I can't combine those terms. And so now we look at the domain. So if we look at each domain separately, the domain of f here goes from 0 to infinity, because we have the square root of x, so that's going to be from x greater than or equal to 0. And then the domain of g is negative infinity to positive infinity. So if we look at these two domains, what they have in common is going to be from 0 to infinity. And we can see here, since I have a square root of x, then the domain for the square root of x, remember you take the radicand, which is the number inside or the variable inside, and we set it equal to 0. And at this point, this is where the domain begins. Okay, so my domain is going to be from 0 to infinity. Let's try the next one. So we have f minus g of x, and I can rewrite that as f of x minus g of x. So f of x is square root of x minus g of x, which is x minus 13. Simplify. So I get square root of x, distribute the negative, Negative negative is positive 13. Again, since I have square root of x, my domain is going to start from 0 to infinity. Letter C, f times g of x is the same as f of x times g of x. So f of x is the square root of x times g of x. So if we simplify, distribute this in here, so we get x square root of x minus 13 square root of x. The domain, you have square roots here, so the domain will start at 0 and go to infinity. And last, we have the quotient. So this would be f of x divided by g of x. So f of x is the square root of x, and g of x is x minus 13. I can't simplify further, so my answer here is the square root of x divided by x minus 13. So if we look at this problem, do we have a fraction? Yes. So for this square root of x, the domain here, for the square root of x, the domain starts at 0. And then for x minus 13, we have a fraction. So remember we set the denominator equal to 0. So x is equal to 13 can't be in the domain. So what this means is that the domain is going to be everything that starts from 0 to infinity with the exception of 13. So we can write that from 0 to 13, union 13 to infinity. Okay, the next one. We have f of x equals x minus 5. And g of x is x squared minus 1. And we're trying to find the product. So the product here is going to be f of x times g of x. So f of x is x minus 5, and g of x is x squared minus 1. Multiply this out. X times x squared is x cubed. X times negative 1 is negative x, minus 5x squared plus 5. Gather any like terms, which we don't have, so this would be our answer. So for extra credit on quiz 2, I'm going to say for 2 points on quiz 2, find the domain. For A, we'll just find the domain. Let's look at B. So f of g of x can be written as f of x divided by g of x. F of x is x minus 5. G of x is x squared minus 1. I can't simplify anymore. So my answer is x minus 5 divided by x squared minus 1. Notice here that we don't have any square roots, but we have a fraction. So we set the denominator equal to 0. Take the square root. So your domain cannot include positive 1 or negative 1. Okay, so we cannot have positive 1 and we cannot have negative 1. So my domain will go from negative infinity all the way to negative 1. Then it starts at negative 1 to positive 1. Then it goes from 1 to infinity. Okay, and you can see that on the number line. We're including all of these except for negative 1. Then we start here, except for 1, and then we go on. Okay, let's go on to the next page. Okay, we'll come to the definitions in a little bit. Example 4, evaluate f of g of 1. So given two graphs, we want to evaluate f of g of 1. So the first thing you want to do is the parentheses inside. So we have g of 1. Here's our function g. The 1 is x. So we want to go to your x-axis, locate 1, and then see where it touches the graph. So we go up, we can see that g of 1 is equal to 3. So g of 1 is equal to 3. Again, we go to the 1, go up, and we can see that it's 3. So f of g of 1 is equal to f g of 1 here. We got 3, so I'm going to replace that with a 3. And now we go to evaluate f of 3. So we go to the function f. X is representing 3, or 3 is representing x. So we go to 3, and then we see where it touches the graph. So if we go up, that's going to be at 6. So that's going to be equal to 6. So f of g of 1 is equal to 6. For example 5 and 6, we're going to be looking at something called the composite function. When the output of one function is used as the input of another, we call the entire operation a composite of functions. For any input x and the function f and g, this action defines a composite function, which we write f composed with g. So this open circle here doesn't represent multiplication. This open circle represents the composition. So we read this as f composed of g. The domain of the composite functions is all x such that x is in the domain of g, and g can change. Basically here, it's the domain of the second function. In this case, it's g. But if you had h of f, then in this sentence here, I would say in the domain of f. So it's always going to be the second function. It is important to realize that the product of the functions is not the same as the composition of the functions. Okay, so let's do some examples. So basically, let me draw a picture of what's going to happen. So let's say you have f of x is x plus 2, and g of x is x minus 3. Okay, and then we want to do f composed of g, and let's call this 4. First, we can rewrite this as the first function is on the outside, the second function goes on the inside. And so what's going on here is, let's say you had two machines. This is your f of x machine, and then this is your g of x machine. And so inside of this machine, you have the following x plus 2, and over here you have x minus 3. So what happens is you first want to visit the machine that is in the parentheses. So we're going to work with g of x. And so what we're going to do is we have a 4 here. The 4 is going to replace the x. So anywhere you see an x, we're going to replace it with 4. So we get 4 minus 3, which is 1. Okay, so that's going to be your input is 4, and then this machine gives you an output of 1. So the 1 comes out, and then it's going to go to the next function, in this case f. So it comes around, it looks for the x, and wherever you see the x, we replace the 1. And then this will give us the final answer, which is the composition is equal to 3. Okay, so notice if I reverse this, what if I have g first? Okay, so g of f of 4. Then if you still have your two machines, this is f of x, and this is g of x. So f of x, we have x plus 2, and g of x, we have x minus 3. So first, we would visit the inside function. So this 4 is going to go to the function f, look for the x, substitute the x with the 4. 4 plus 2 is 6. This is your output, and now it's going to visit the second function. So wherever you see the x, it replaces that x by that output. 6 minus 3 is 3. So G composed of f of 4 is equal to 3. In this situation, we get the same answer, but that's just a coincidence. You're not always going to get the same answer. So if it helps, you can make a picture like this when working with the problems. Given f of x, x plus 4, and g of x is x minus 8, find each of the following. So first, you want to rewrite this the way it's defined. So f composed of g of 1, the first function goes on the outside, and then the second function goes on the inside. So we want to evaluate g of 1. So that means that we're working with a g function. The g function is x minus 8. And so for the 1, we're going to substitute, for the x, we're going to substitute the 1. So 1 minus 8 is negative 7. So now that we have a negative 7, now we're going to work with the f function. So the f function here, we're going to plug in, for the x, a negative 7. So we end up with negative 7 plus 4, which is negative 3. So f composed of g of 1 is equal to negative 3. Okay. So again, the way we do this is first we input the 1, and for the g, so 1 minus 8 gave us a negative 7. Then we take our negative 7 and plug it in for the second function. Negative 7 plus 4 gives us negative 3. Okay, on this one we can write it as g of f of x. So first we do the inside. So we go to the function f. Wherever I see an x, I'm going to substitute it with this x. So this x right here is going to go and be substituted for this x. So if I plug in x here, I get x plus 4. So f of x is just x plus 4. And now I'm going to take this information and go to the function g. So all of this is going to come, and we're going to substitute it for that x. So for this x, I'm going to write x plus 4. Then I have minus 8. So the composition of g composed of f is x minus 4. And then the last one here, we can rewrite this as f composed of g of x. And so here we want to do the g of x first. So g of x is just going to be x minus 8. And now we want to do f of x minus 8. So we're going to take all of this and plug it in for our function f for x. So if I plug in for this x, I'm going to plug in x minus 8, and then I have a plus 4. So we get x minus 4. So the composition is x minus 4. Example 6, given f of x is 2x plus 4 and g of x is x plus 4, find g composed of f of 3. So we get g composed of f of negative 3. So first, you want to do the function f. So we want to evaluate f at negative 3. That means we're taking this negative 3 and plugging it in for the x in the function f. So we get g. If I plug in this negative 3 in for the x, then I get 2 times negative 3 plus 4. Negative 6 plus 4 is negative 2. So now we want to plug in negative 2 in for the function g. So here's my x. So I'm going to have negative 2 plus 4, which is positive 2. So my answer for g composed of f of negative 3 is equal to positive 2. Okay, let's go to the next page. Given f of x is 5x plus 6 and g of x is 2x squared minus x minus 1, find the composite function and then find the domain of each function and the composite function. Okay, so first we need to find the actual composition. So I'm going to write it on this side. F of g of x is written as f of g of x. So first you want to do the inside of the parentheses. So here we get f g of x is given by this right here. So that's 2x squared minus x minus 1. And now we need to evaluate the function f at 2x squared minus x minus 1. So that means that we're taking all of this and plugging it in for this x in the function f. So here we get 5 times 2x squared minus x minus 1 plus 6. Simplify, distribute this 5 inside. So we get 10x squared minus 5x minus 5 plus 6. So this is 10x squared minus 5x plus 1. So the composition is equal to this right here. Then it says to find the domain of each function. So the domain of f, notice here that this is just a line. So my domain would be negative infinity to positive infinity. There's no fractions, there's no square roots, and there's no logarithm. So the domain is always negative infinity to positive infinity. And then the domain of g, is there any fractions? No. Square roots? No. Logarithms? No. This is a parabola. So it's going to open something like this. So which will use all the x values. So negative infinity to positive infinity. And then it says to find the domain of the composition. So we look at the definition. The domain is x such that x is in the domain of g, and g of x is the domain of f. It is important to realize that the product of the functions f of g is not the same. Okay. So this is the important part. The domain is going to be x such that x is in the domain of g. So the domain of g, remember I said it's the second function that you have here that we have to take an extra look at. So To find the domain, we can write this in two steps. Number one, find the domain of each function, which we did right here. Number two, identify the second function listed. So for example, in our example here, we have f composed of g of x. So the one that we're going to focus on is the second one here. So the domain of g is negative infinity to positive infinity. Then we're going to find the domain Then we're going to find the domain of the composite, which is your answer. So my composite was (10x² minus 5x plus 1). So if we look at this answer, this is a parabola, so the domain is going to go from negative infinity. So I'm going to write this as a composite, negative infinity to positive infinity. So your domain is going to be the intersection. In other words, what they have in common for step 2 and step 3. Okay, so here the domain of g is negative infinity to positive infinity. So that's what we get for step 2. And then for the domain of the composition, we get negative infinity to positive infinity. So we ask ourselves, what does this have in common with this? Well, they have everything in common. So the final domain of the composition is negative infinity to positive infinity. So we always need to make sure that we're checking step 2. And you'll see why it's important in the next example. So f of g composed of x is f of g of x. So if I plug in g of x is 1 over x. And now everywhere I see x in the function f, I'm going to replace with 1 over x. So we're taking this and plugging it in for this x. So we end up with 4 over 1 over x plus 2. We want to simplify. So one trick here that we can do, well, one way to simplify this is to add these two together. So you would have to find a common denominator and then divide 4 divided by that. Or we can multiply every single term by the denominator here. So I'm going to multiply this by x and this by x. So this becomes 4x divided by x times 1 over x is 1 plus 2x. So my composition is equal to 4x divided by 1 plus 2x. Okay. So to find the domain, again, the first step is determine the domain of each function. So here the domain of f, since we have an x plus 2, we set that equal to 0. So negative 2 can't be in the domain. So my domain will go from negative infinity to negative 2 union negative 2 to infinity. And then for g, Here's g. X is a fraction, or 1 over x is a fraction. So we set the denominator equal to 0. So 0 can't be in the domain. So this domain will go from negative infinity to 0, and then 0 to infinity. And then the third domain that we need is the domain of the composition. So notice that the composition has a fraction. So we set the denominator equal to 0 and solve for x. So subtract the 1 and divide by 2. So negative a half can't be in the domain. So my domain will go from negative infinity to negative a half, union negative a half to infinity. Okay. So now to find the actual domain, we want to look at the intersection of the second function. In this case, the second function is g. So I'm going to look at g. So I'm going to look at g, and then I'm going to look at the intersection of the composition. Okay. So we want to see what they have in common. So I'm going to draw a little picture here. So the domain of g is everything except for 0. So it's everything here except for 0. And then the domain of the composition is everything except for negative a half. So here's negative a half, and then it takes everything. So you want to see what they have in common. So what they have in common is basically we cannot use 0 because 0 cannot be used for the first one. It can be used for the second one, but not the first one. So 0 is not common to both. And then negative a half cannot be used for the first one. So since it's not in both, then we can't use the negative half. So my domain is going to be everything except for 0 and negative a half. So I'm going to go from negative infinity to negative a half, union negative a half to 0, union 0 to infinity. Okay, so again, if I draw a better number line here, this is for the domain of G. It's everything except for 0. And then for the composition, it's everything except for negative a half. So we're going to use all of this, but when we get to negative a half, we cannot use it. And then when we get to 0, we cannot use it. So example 9, write f of x equals x minus 2 squared as a composition of two functions. So now what they want us to do is find two functions. And when we do the composition, it should produce this answer. Okay, so if you notice here, we have something in the parentheses and then we have a square. So whatever's in the parentheses, we can call that one function. And then the outside, we can call that something squared. Well, that's something, we can just call it x. So these will be our two functions. And now we need to figure out, is it going to be g composed of h of x, or is it h composed of g of x? Yep, so we can test them. So here I get g of h of x. So if I was to plug this in, I get g h of x is x squared. And then I would plug in x squared in for my x. And so that's going to give me x squared minus 2. And this is not the same as our answer here. So this one doesn't work. And if I check this side, then this one should work. g of x is x minus 2. And if I plug this in for my x here, then I get x minus 2 squared. And that is what we have as our answer. So my answer here is h of g of x, but the way we're separating this is a function g and this is a function h. Let's try another example. F of x is equal to absolute value of x plus 5. And we want to find two functions. So whatever's in the inside of the absolute value, you can call that one of the functions. And then the absolute sign, you can call that your second function. Well, the inside of the function is always going to be that second function here. So I can say, okay, that this is going to be g composed of h of x. And then you can check your work to make sure it does work. So h of x here is x plus 5. If I plug in x plus 5 for x, then I get absolute value of x plus 5, which is what I had in the original. But if this didn't work, then you can try h of g of x. Okay, so that was it for section 1.8.